Hello everybody, welcome to Rational Science. Today we're going to talk about LIGO. LIGO in this interferometer that was built around 1986 and onwards, and looks something like this. Okay, it's about 2.5 miles long, 4 kilometers, each one of those arms. Okay, and why did I pick on LIGO? Well, because in the year 2017, these people won the Nobel Prize, okay, in so-called physics, mathematical physics, okay. It says October 3, 2017, that's when it was issued. The Royal Swedish Academy of Sciences has decided to award the Nobel Prize in Physics 2017 with one half gold medal, okay, gold medal winner here, to Rainer Weiss, okay, and from the Ligo Virgo collaboration, and the other half was divided between two gentlemen, Barry Barish and Kip Thorne. Okay, and for what? Well, for decisive contributions to the LIGO detector and the observation of gravitational waves. That's what it was all about, to detect gravitational waves. Okay, so let's go into more detail. What was this project about? What did these people get the Nobel for? Well, here it is from the Nobel site. Gravitational waves finally captured. Okay? On September 14, 2015, the universe's gravitational waves were observed for the very first time. The waves, which were predicted by Albert Einstein 100 years ago, just coincidentally, 100 years, right? Came from a collision between two black holes. It took 1.3 billion years for the waves to arrive at the LIGO detector in the United States. That's already a little bit fishy for me. Let me tell you why. 1.3 billion years, okay? They travel at the speed of light, so whatever it was, I guess these two black holes were 1.3 billion, okay? Light years away, okay? Now, gravity is known to be a function of the distance, okay? So you would think that a collision between an asteroid and Mars or an asteroid and the moon would create a more powerful gravitational wave than something, whatever it is, doesn't matter what, which is 1.3 billion light years away. Food for thought, okay? Anyways, the signal was extremely weak when it reached Earth, but is already promising a revolution in astrophysics. Well, the wave came and went, and we still have no revolution. I'm still waiting for the revolution, okay? Maybe they were referring to some kind of something related to politics. I don't know. Revolution, overthrow the Russian government. I don't know. LIGO, the Laser Interferometer Gravitational Wave Observatory, is a collaborative project with over 1,000 researchers from more than 20 countries. And they did not mention, but it was $1.1 billion spent by the time of the Nobel. So that's how much we spent to detect gravitational waves, okay? Pioneers Rainer Weiss, Kip Thorne, together with Barry Barish, the scientist and leader who brought the project to completion, ensured that 4 decades of effort led to gravitational waves finally being observed. And yeah, actually it was more like 5 decades, because it was like the end of the 60s, 68, 67, thereabouts, when the idea of this interferometer to catch gravitational waves was being developed. So right now you're talking about 50 years. And during those 50 years, especially after, I think it's 1986, they started spending money on it, real money, and by the time of the 2017, when they allegedly discovered the gravitational waves, they had spent $1.1 billion. Okay? So the issue is whether that money was well spent. That's one issue. The other one is it's kind of coincidental that they discovered these gravitational waves that Einstein predicted in 1916 originally, and they discovered it almost 100 years later. Just the centenary of Einstein's discovery. Quite coincidental. I'm sure Einstein would have been very proud. And the other issue that you got to think about is that what would have happened if they spent all this money and 50 years and discovered absolutely nothing? A lot of people would have been a little pensive. They would have been thinking about this. You mean you spent $1.1 billion. What do we get in return? Nothing. No, they had to discover something. Okay, they absolutely had to discover something, or otherwise they would have canned the project. Okay, and of course the Nobel always helps, right? Because it's prestigious, and you get the Nobel, and suddenly you get, all this publicity, and people become, what did we say last time? Rock stars. Okay, these celebrities, people whom nobody knows, suddenly become rock stars, and they get interviewed, and suddenly it's a big deal. And again, I'm waiting for that revolution. I don't know what revolution this caused in physics, science, or whatever. Maybe in mathematical physics. I don't even think it caused a revolution there, because everybody's moving on to string theory. They're not looking at gravity waves. They're looking at gravitons falling into black holes. So I'm not sure where the revolution is. Maybe it just passed me by and I missed it. Okay. Anyways, yeah, they finally observed the gravitational waves. Or so they say, right? Because that word observation also is quite nasty. It's quite misleading. When people say, I observed, you would think they kind of use their eyes, to see something. That's not the case here. Not even by a long shot. Okay. No, when they say observed, they mean that they interpreted. That's what they mean by observed. They interpreted. Okay. They surmised. They inferred. That's what observation means. It doesn't mean observe like with two eyes. Okay. You can't observe gravitational waves. But when you put the word observe in there and you get a Nobel for it, well, yeah, it kind of convinces people that those people know what they're doing. They saw the wave go by. Like you see a water wave from the ocean. You see the waves. You say, well, I observed the wave. When these people say, I observed the wave, they say, oh, geez. So they saw it floating by. Okay, so you got to keep all this in mind. That's how they publicize all this stuff, right? Let me keep these guys in there. There we go. So who are these people? Okay, here's the first one, Mr. Weiss. Okay, and he's born in Germany originally, but he went to the United States very early in life. And he's the head. He was the head, he was the head, because the head Kobe is no longer around. But he was the head of Kobe that measured the CMBR. So he was always into these cosmic measurements. Okay, he invented the interferometer, the one that's used by LIGO. And so in that sense, that's the reason he got the gold medal, and the other guys got bronze and silver and whatever. And he's also now a member of Fermilab holometer. Okay. Experiment uses laser interferometer to measure space-time and holographic fluctuations at quantum scale. Okay, so that's what he does for a living. Okay, that's whom you're paying his salary to. Okay, here's another. The second fellow, he got a silver medal, I guess, or maybe split the bronze or split the silver. I don't know. He's essentially an experimental lab tech. Okay, he was the head of LIGO for almost since inception essentially in 1986. That's when it really got started. He came in a few years later, but he took it to completion. Okay, he's now head of the International Linear Collider. Okay, and essentially he's trying to build an accelerator that accelerates particles at the tera electron volt scale. That's an energy level higher than what we have today at the LHC. So they serve, or the intention is to serve as a complement to the LHC. Okay. And then the third guy, he's a little more famous than these two guys. For all of you who've been in mathematical physics for a while, his name is Kip Thorne, and he's a theoretical mathematician, expert in all kinds of holes, like black holes and wormholes, and their applications, or cosmic applications in general, of GR, general relativity. More important than that is whom you know, and he was a longtime friend of Sagan and Hawking, Carl Sagan and Stephen Hawking. And that was very, very important for him and for his career. And he also contributed or helped out with a script in the movie Interstellar. What's his contribution to LIGO? Well, he calculated the gravitational wave strengths, and he also proposed how to detect the gravitational waves. Okay, he said that evidence would consist of fluctuations between two or more static points. And that's essentially what they did with LIGO. Okay, they looked up in the sky and they said, "Look, what's up there?" Well, they said, "Well, we need big masses like black holes, you know. So they took two locations very close to each other, and from there, assuming there was a collision, which is what they suggest happened there, they received the waves here. And that was essentially what Kip Thorne suggested to the LIGO people, okay, in a nutshell. Okay, where did he get this idea of gravitational waves? Well, he got it from Albert. Who else? I mean, if you're going to do something, you better name the key person. The key person here was Albert Einstein. So he came up with a theory, essentially his thesis in originally in 1916. This is his 1918 paper in which he amended his 1916 paper, allegedly because he made some mistakes, some mathematical mistakes, and so he corrected them allegedly in this paper, okay? And here's his original paper, okay? This is what it said, and essentially this is what came out even after 1918. And it says the following. It says, this is his reasoning. He says, oscillating charges give rise to electromagnetic waves. Therefore, oscillating accelerated masses also produce waves. However, gravity is a weak force. Okay? You've heard about that maybe on and off, that some of these waves are very hard to detect. And why? Because, you know, electromagnetism is a stronger force. Here you have a statement from an article that came on New Scientist. Gravity mysteries. Why is gravity so weak? Gravity acts over vast distances, but why is it such a weak force? And so they explain, it says, your puny muscles weighing just a few kilograms can overcome the gravitational force of the Earth. All 6 times 10 to the 24th kilograms of it. Gravity is a real weakling, 10 to the 40 times weaker than electromagnetic force that holds atoms together. So far, our best explanation comes from string theory, the leading candidate for a theory of everything. String theory requires that the universe has more than 3 spatial dimensions that we experience, and possibly as many as 10. Well, we talked about that in the past, right? 10 dimensions? Yeah. According to string theorists' best ideas, gravity is so weak because, unlike the other forces, it leaks in and out of these extra dimensions. Okay, so these guys, the string theorists, they work on dimensions. These other fellows, they would rather stay within the 4 dimensions of space-time and say that these are waves that come from, in this case, collision of 2 black holes. And they continue to say, we only get to experience a dribble of the true strength of gravity. The proof of this might come through experiments that probe the gravitational attraction between objects that are very small distances apart. String theory suggests that the unseen dimensions are hidden from view because they are rolled up small and lie end on to our dimensions, making it hard to detect their presence. No, they're never going to be able to detect these waves, okay? Why? Because they're talking about these dimensions. I mean, because they're talking about 90. What is a dimension? It runs 90 degrees to another dimension. And we can imagine all 3 of them, you know, length, width, and height. And then from then on, we run into trouble. You cannot imagine a perpendicular line going perpendicular to all those 3. There's no way you can imagine that. Much less can you imagine, 10 dimensions perpendicular to each other? Of course, no one can imagine that. That's why they treat it mathematically. Anyways, continuing here. Therefore, because it's a weak force, it's unlikely to be detected, according to Einstein. Even a binary star system would not have the mass necessary to produce detectable waves here on Earth. What is needed is revolving stars with extremely heavy masses that are separated by short distance. And how did LIGO come into play? Well, they said, hey, black holes. See, in the days of Einstein, especially in 1915, they didn't have too many ideas about black holes. The black hole idea was just starting out with Schwarzschild's paper at the end of, 1915. Yeah, I think it was 1915, maybe 1916. I can't remember exactly now. But one of those 2 years, they came up with a black hole idea. But it was treated as it's an interesting thing, you know. No one put their hand in the fire for the existence of black holes. No one believed in black holes at the time. And so Einstein said, you know, we could detect these waves if we had heavy enough celestial objects out there, like 2 stars that are revolving around each other because they're a binary star. But he says, you know, the mass that you would need out there is so huge that, you know, stars won't do it. And so LIGO came in, you know, about almost a century later, and they said, hey, but what about black holes? Now we have proven the existence of black holes. All we have to do is detect waves coming in from a collision of 2 black holes. And that's what LIGO was about. And so they prepared this interferometer, which is essentially a bigger model, much bigger model than the one used by Michelson and Morley to so-called prove that the ether doesn't exist. Okay. So here's the summary from the same group in the Nobel Prize winners, from the Nobel Academy or organization. Gravitational waves spread at the speed of light, filling the universe, as Albert Einstein, you got to give credit to Al, okay, described in his general theory of relativity. They are always created when a mass accelerates, okay, like when a pair of black holes rotate around each other, okay. Einstein was convinced it would never be possible to measure them. The LIGO project's achievement was using a pair of gigantic laser interferometers to measure a change thousands of times smaller than an atomic nucleus as the gravitational wave passed the Earth. Gravitational waves are direct testimony, evidence, to disruptions in space-time itself. So we're talking about what, the waves of space-time, I guess, yeah? A wealth of discoveries awaits those who succeed in capturing the waves and interpreting their message. We have a message in a bottle coming through the ocean of space-time, and he who catches the bottle, he wins a Nobel. That's more or less what they're saying here, okay? So many problems. So many problems. And let me tell you, here's a couple of them, okay? Let's go with some of the problems. Here's the first one, okay? This is what Einstein's suggesting. He said that gravity, originally he had an idea that there were two types of waves, the longitudinal and transverse waves, but then he said there could be a third type of wave that carries no energy. But then he was dissuaded from that by colleagues, and when he wrote his new paper, the one in 1918, he said, look, gravity waves are transverse waves. You know, there you see a transverse wave, okay? And the question is, you know, what is a transverse wave? What is it made out of? What is vibrating? What is waving? That's the first. There is no standalone object called wave. You should not ever talk about waves, okay? Because waves, you got to identify what the object that is waving is. That's where the key is. But if you just say wave, well, you know, what are you saying with that? Okay, and let me give you, for instance here, an example. Okay, you have a wave. Okay, how do you pull with a wave? In other words, if I were to drop this ball, okay, see the ball? I'm gonna let it drop, and it falls, in this case, towards the table. Okay, and the question is, how did the table or the ground or the earth attract the ball downwards? Obviously, it's not falling upwards, right? It falls always downwards. You can do the trick at home. You know, you don't have to believe me, but take any ball, baseball, whatever, football, and just let go of it, and you'll see that it falls to the ground, not to the sky, to the ceiling. Okay? So the question is, why does it fall to the ground? That's all we need to figure out. These people are saying, or Einstein was saying, transverse waves. Okay, so transverse waves. Tell me how a wave that goes one way, travels one way, for example, from the earth to the ball, how does it attract the ball? You want it in reverse? You want the ball sending the wave to Earth? Fine. How does sending a wave one way attract? Produce this pull, this attraction towards my table of this ball. Okay, that's what you need to explain. So okay, so they detected the wave, so-called gravitational wave. Keep that in mind. Gravitational, right? Okay, so the wave comes over. They have this interferometer. They detect it. They say, okay, we found the wave. We detected the wave. We observed the wave. Fine. Tell me how that wave attracts you. How does that wave attract the Earth? Did it move the Earth closer to the two black holes that were colliding? Did it take it out of Earth's orbit by an inch, by a millimeter? I mean, this wave comes over, and they say it passed the Earth by. Yeah, I'm sure it did, because it's like a wave in the ocean. You know, if you have a telephone post there, you know, and the wave comes over, the wave goes by, but the telephone pole does not get sucked into the middle of the ocean. Okay, so the question is, how does this wave that comes over pull? In fact, if anything, it pushes, right? So if it pushes, it's not attracting. So what is this wave that comes over here and we detect it, but we don't have a mechanism why is it gravitational? I mean, gravitational is supposed to pull, and this wave just passed us by. So you can see there's a little bit of a problem with the so-called gravitational wave. That's one issue. Now, there's another issue that you should be aware of, and that's first, a lot of people give Einstein credit for everything, and for black holes, for Big Bang, for gravitational waves, and so on. And here you, what happened here? I had a thing there. Anyways, Einstein didn't believe in waves, in black holes. Einstein did not believe in black holes, and so the question is, they're going to use Einstein for the waves. Are they going to use Einstein for the black holes? And what they say in that case, well, Einstein was overruled. Here's the pastor of relativity, right? The number one head honcho of relativity, and they're going to overrule the pastor, saying, well, he did not know that black holes exist. In fact, what I was going to show here is that he wrote a paper in, I think, 1939, in which he said that black holes don't exist in reality. Okay? And so if black holes don't exist, according to Einstein, right, because he knew his equation just about as well as anybody else, he says black holes don't exist. And so what is it that these people saw that they say two black holes collided, and that's what produced the waves? And these two black holes were, what, 1.3 billion light years away. And again, I would think that an asteroid crashing against the moon, which is over here right at the corner, okay, drugstore, you would think that a collision there between that would create a stronger gravitational wave than whatever at 1.3 billion light years away. So again, Einstein saying there's no black hole. That's why he gave up on the notion of the idea that you could ever detect the gravitational waves. These people say, no, we discovered black holes, and now we build this interferometer, and that's going to capture, if there happens to be a collision out there between two black holes, which have the mass necessary for the equations to be able to deal with them. Okay? And so that's what happened, according to these people. They say, look, two black holes collided, they created these gravitational waves, and they reached the Earth. We were able to detect them with these very sensitive interferometers, and from there they extrapolated that what created those waves was the collision of two black holes. Okay? Now, the first thing you have to think about also is, were those the only two black holes in the universe that collided? I mean, you would think that they say there's a black hole in the center of every galaxy, and they're all over the place, everywhere in the universe. So you would think there are more collisions than just one happening 1.3 billion light years ago, right? So if there are more collisions, we should be receiving waves from every part of the universe of collision between black holes. They only detected one after, what, 50 years? Makes you stop and think, we should be receiving more waves from more collisions. And, again, you would think that a collision between something a lot closer, even though it doesn't have the same mass as a black hole, would create waves that we would be able to detect much easier than something very heavy 1.3 billion light years away. Okay, so these are some of the problems that I see with all this. Okay, just in case, we showed the other day that there is no such thing as a black hole. Here you had a statement, this comes out of Hawking's book, A Brief History of Time, and he said Eddington thought it was simply not possible that a star could collapse to a point. Einstein himself wrote a paper in which he claimed that stars would not shrink to, what? Zero size. So what is a black hole? Zero size. Maybe not all of them, but certainly a lot of them. And if you have one black hole that is zero size, we have a problem, because that means that you have nothing in front of you, and these people are saying that it's got a lot of mass but no structure whatsoever. It's got no volume, no diameter, no radius. There it is, zero size, zero radius. I like to put some evidence there always, because people say, well, maybe they said that you're taking it out of context or something, whatever, And here's again another couple statements. This Chaudhuri, he's an Indian physicist, mathematical physicist. He worked in the West. I think he worked in Cambridge. He also published his book there. And he says, R. What is R? The radius R. R falls to zero size. That's what Chandrasekhar proved. Okay. And then other statements like this fellow, he's a teacher, a professor at University of Toronto. He says matter is crushed out of existence. In this case, he mentioned neutrons, but you'll see that constantly everywhere. Matter is crushed out of existence inside a black hole. Okay, so I don't know what these people are talking about when they talk about black hole. If they're talking about zero dimensional, zero volume, zero radius, there's nothing there. And they're saying, well, there's no structure, but what you have is mass. The mass remains behind. The elephant was crushed out of existence, but his 5 tons remains. That's what these people are saying. Why? Because it's a mathematical concept. They can deal with that mathematically. Of course, they can't deal with that physically, and you cannot even imagine just 5,000 kilograms sitting there, okay, of the elephant. You cannot imagine, because what do you have? Just kilograms? That's it? And so these people work with kilograms. They want to insinuate that there's something there. But that something is zero-dimensional, meaning there is nothing there except the mass. That's a bunch of mathematical gibberish. It has nothing to do with physics. Okay, let's be straight about that. Okay. Anyways, here's the argument I always make, that the black hole is circular. The notion of black hole. Why? Because a black hole only has mass. It has, some of them have, they claim, not all of them, but some of them, or most of them maybe, have charge and angular momentum. But all of them have mass. All of them have mass. That's what a black hole is made of, mass. Mass is the quantity of matter. That's what people understand by mass, and they don't have a definition other than that, really. And black hole crushes all matter out of existence. So what do we have? We have a circular argument. That's what we have. We have, there is no such thing as a black hole. And so you wonder what all these people are spending their time and your money on, with this black hole stuff. You're investigating black holes, calculating stuff on black holes, when what does it have to do with reality, with physics? Okay, that's what you have to ponder here. Okay. Anyways, here, let me give you try to imagine, here's a thought experiment for you. Okay. We're going to have a star that's going to turn into a black hole. Okay. I want you to try to visualize this. You're going to have the star, it's going to turn into a black hole. We're going to look at the atoms way in the center of the middle of the star, right in the center of the star. Okay. What happens to them? According to these people, the star shrinks, collapsing by its own gravitational weight, right? So it compresses the atoms in the center, and one of the two, it either crushes them out of existence, or it makes them smaller and smaller and smaller and smaller and smaller until there's nothing there, you would think. How small can you crush an atom? I mean, it's already small. Beyond the Planck length? Are you going to make this thing collapse to something unimaginably small? How small can this atom be? I mean, if you take a very massive black hole, let's just to be on the safe side, 1 billion times bigger than the sun, and it collapses on itself, gravitationally collapses on itself, right? What does it do to the atoms in the center of that star? Well, I don't know. It's got to pulverize them. They shouldn't exist anymore. And that's why, these people who talk about crushing matter out of existence, they're saying the right thing. If that's the case, it should crush matter out of existence, right? And so what's left? If you crush these atoms, if you compress them so much, what happens to those atoms? Do they disappear? Does length, width, and height turn into nothing? What happens to the atom? So that's what I want you to focus on. Here it is. Okay, here you see a sun, a star, right? We're going to look at the atoms in the center. Those are the atoms just in the center of the sun, okay, of that star. And so let's look at those, okay? And now we're going to crush them even further, because remember, you've got other atoms around these, and they're going to compress these atoms further and further and further, okay? And so here you're going to get an idea of what I'm talking about. Here you see them being collapsing, right? They're being compressed slowly, but surely, or maybe fast, I don't know. But the question is, they're going to be compressed until what? How small can they get? Are they going to go beyond the Planck length? Is that what the people are saying? Or are they going to disappear completely? And if they disappear completely, why will the mass remain? The mass of that atom remain behind? Because mass is related to the atom. Atoms have mass. That's like the basic unit, the building blocks of all matter. And here you're talking about, and in this case I just used hydrogen atoms for simplicity's sake, you're crushing this thing, right? Okay, let's assume that's the case. You crush. How small can you make the atom? Infinitesimally small? It's still there? It still has all the mass? Or does it compress it out of existence? And so the question is, how much can you squeeze these atoms and still maintain your sanity in mathematics? These people are crushing these things and not worrying about the physicality of the atom. They're saying, yeah, we crushed it, and here's the mass. Let me tell you about the mass. I don't care about the mass. I want to know what happened to the atom. Atom is a real thing. That's what has to do with physics. So if you're going to crush that atom, I want to know if you crushed it out of existence, by what mechanism? Where did it go? Or did it turn into space? Is that what it is? Is it the vacuum? Or is it still there, just tiny, 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 and getting smaller and smaller and smaller as it's being compressed further and further and further by all the matter around it? So these are the questions these people have to answer. Those are questions of physics. These people want to talk about, mass and kilograms. They want to talk about math, calculations. We don't care about your calculation. We want a physical interpretation for what's going on inside a black hole. Don't give me an equation because it has nothing to do with reality. I need to know what happens to the atom. Is it crushed out of existence, or is it just tiny, so small that, and it still in that case would retain its mass? If it's crushed out of existence, first by what method, and then does it retain its mass when mass is a quantity of matter, meaning quantity of atoms, and you're saying that the atom was crushed out of existence and turned into space, but the mass remains behind? These are the questions these people have to answer. That's the problem. Okay. So for these people to go around and say, oh, look, we've calculated the mass of a black hole, and it's got to be this big because we can see stuff revolving around it or being sucked into it or whatever. That's an inference that they have. They don't have any proof other than their equation saying, look, here's the equation. Yeah, that's if there's something in the center there. And if there's nothing in the center of that orbit, if there's nothing there that is sucking the skin of a star, then what are you talking about? So the black hole is an assumption. But the assumption is wrong because they don't have a definition for a black hole. Black hole supposedly is a star that collapsed upon itself and turned into nothing, 0 dimensions, so we have nothing there, but the mass remains still in that region of space. Again, it makes no sense whatsoever in physical terms. And for these people to develop an interferometer, 1.1 billion spent on it, over 1,000 people working on this stuff today, that's your money. See, what they do is they go to the politician and they say, look, we need money. We need money for the LIGO, the interferometer. And the politician, maybe knows a little bit about science. And he says, well, justify it. What do I need to, what is it for? Well, we're going to detect gravitational waves. Well, he doesn't know probably what that is. Probably doesn't even care. He says, okay, and what's that good for? Is that going to develop anything for us? Well, in the process, we're going to develop technology. Okay, that's one issue. That's one sweet point that they mentioned. And the other one is, we confirmed Einstein's theory for the gazillionth time now. We're going to confirm it one more time. Okay. And so the politician says, well, okay, here's the money. So he gives them the money, and that money is your money. He's your representative. Okay. But it turns out that it only gets better, see, because one of the things that you'll find is that the LIGO, you would think, is it over? They've detected the gravitational waves. Okay, let's pack our bags. We're done. We spent the money for whatever reasons. Now we can move on. No, we're not moving on. What they're doing now is creating another LIGO in India, which is being sponsored or funded by the United States, Australia, and the UK, okay, among other countries. I don't know if there are other countries involved there. I think they are. And now they're building another LIGO over there, and they're going to be building some of these LIGOs like they're building accelerators. They want to build these LIGOs all over the world to form some kind of a network so that they can detect more gravitational waves in the future and confirm Einstein theory for the gazillionth time. So this hasn't stopped. Quite the contrary. That Nobel Prize in 2017 just gave them more fuel to go to politicians and say, oh, keep giving us more money because now we're building one in India. We're all supporting it because it's part of the same network. And we're going to be building some more of these guys so that we can have a network that collects gravitational waves from every black hole in the universe that collides out there. That's where they're headed. And so, yeah, you got to think about what these people are doing and whether it's worth your money. This is what they're spending their money on. This is what they're spending their mathematical talent on. This is what they're developing. And these are the guys, from quantum and general relativity. On the other hand, you got the string theorists. They've abandoned all that stuff. They think quantum is at a dead end, and they're developing equations that have to do with gravitons falling into a black hole and having the surface of the black hole projecting holograms. So they're studying the surface of black holes, not because they saw a black hole, but because they say, by studying what happens at the periphery of a black hole, which is where all the matter is falling in and out, coming out, okay, because now matter also comes out of a black hole. Well, by looking at the surface and analyzing what happens there, calculations, mathematical equations, integrals and derivatives and so on, by looking at that, they can figure out, what's inside of a black hole without having to send an astronaut to fall in one of them. So this is what these guys are doing. The other guys are looking for gravitational waves. Are any of these people, even in the ballpark? I mean, I'll give you a for instance. Imagine that you pay this fellow to go out there, and he goes out there and he measures the flight of eagles. Okay? And so he watches them fly, he calculates things, he gives you all this stuff, right? All this information. And it turns out that Mother Nature does her stuff with turtles, not with eagles. And so the question is, this person's wasting his time doing all these calculations when Mother Nature does it with something else, does it with turtles. These people are the same. These people are calculating all this stuff with black holes, with gravitons, with gravitational waves. And if none of that exists, none of that has any validity whatsoever, has anything to do with gravity or with the real world or with physics, then all this money, all this effort is a waste, 100 years of waste. Okay, so that's what you got to think about. These people are making lots of money. They're taking care of their pet peeves. They're going to the politicians asking for money, which is given to them. They've got all these projects out there. What is it all for? Where is the famous revolution? Okay. Anyways, again, what you got to figure out, here's the last point here again. Here's a gravitational wave, transverse wave, as Mr. Einstein said. Tell me how that wave pulls from the right. Okay? It's going one way, it's going towards the right. How does it pull from the right if it's a gravitational wave? So if you detect this eagle flying to the right, what does it matter if Mother Nature does gravity with turtles? Okay? Again, waste of time, big waste of time.